right, I've got a problem up here that's another optimization problem. I want to find the point on the line y equals x plus 1 that is closest to the origin. So the line x plus 1 has a y-intercept of 1, slope of 1. There's my line right there. I want to try to figure out what point on this line is closest to the origin. I can tell it's going to be somewhere around in here, but I'd kind of like to figure out exactly where that is. Okay. What I need to do is translate this into what is the thing that I am trying to maximize or minimize. If I'm looking for what's closest, I'm trying to minimize a distance. Okay. So if I let d equal the distance from a point on the line to the origin, my goal is to minimize this. There's a nifty trick though. I'm going to let capital D be d squared, be the square of the distance from the origin. Okay. And it turns out, since I'm working with distances, where distance is never negative, okay, if I look at this would be like d and this would be capital D, which is d squared, the smaller d is, the smaller little d is, the smaller big D is. So if I want to minimize the distance, it suffices to minimize this. And that's a nifty trick to know when you're dealing with positive quantities. If you want to minimize something, minimizing its square is sufficient. Usually, squaring something makes things more complicated, so I don't want to do this. But I know that when I calculate distances, there are square roots involved. So squaring a distance actually makes it simpler. Okay. So I want to sort of take advantage of that. So, I wanted to give you that trick. I'm going to encourage you now to pause the video, try to work this problem out on your own, and then come back and check your work. Welcome back. Okay. So, if I have a point on this line, x comma y, we're talking about trying to minimize that distance from the origin, and we already discussed we're actually going to minimize the distance squared. So the distance from the origin is just root x squared plus y squared, just using the distance formula, or thinking just in terms of the Pythagorean theorem, where d is the hypotenuse of that right triangle. The leg here is absolute value of x, and this leg would be the absolute value of y. Okay. So that means capital D, which is what I was calling d squared, is just x squared plus y squared. Okay. So that's the thing that I want to minimize. So I'm going to make a note. I want to minimize this. And then I want to say, what is my constraint? Well, the constraint is that I wasn't just trying to find the point that's closest to the origin, because that would be the origin. I was trying to find the point on the line that was as close to the origin. So the constraint is this right here. So I'm just going to say that capital D was x squared plus y squared is going to be x plus 1 squared. I'm going to go ahead and multiply that out. That's x squared plus 2x plus 1. So that's 2x squared plus 2x plus 1. My domain, I'm just going to say the domain is everything from negative infinity to infinity. That's the domain for all points that are on the line. I will point out that I can pretty much see that the point that's closest to the origin is going to be somewhere in between this point and this point. So if I wanted to work on the closed interval of x values that are between -1, which would be where the line crosses the x-axis, and 0, which is where it crosses the y-axis, that would be another perfectly acceptable choice I could make. Okay. Because I can have points obviously over here, but I can see by inspection that the distance from this point to the origin is longer than the distance from this point to the origin, so that's not going to be where I'm going to find my min. Okay. All right, D prime is going to be 4x plus 2. Okay. That is always defined. 4x plus 2 will equal 0 if x is equal to negative 2/4, which is negative 1/2. Okay. So that's my critical number. I'm going to just draw my number line now for D prime. If I had chosen to work on that closed interval, I'd simply create a table of values for the endpoints in this critical number. Okay. All right, if I plug in 0, which is to the, I can plug in 0, but that would be to the right of negative 1/2. If I plug in 0, my derivative is going to be positive. If I plug in negative 1, which would be to the left of my critical number, that's going to make my derivative negative, so I have a min. And again, because we're working with a continuous function, and we have just one critical number, if it's a relative min we get for free, that it's also an absolute min. Okay. So, we were asked to find the point. Well, we found the x value, so the point would be negative 1/2, and then the y value would be negative 1/2 plus 1, which would be positive 1/2. Excellent.